Okay, let's do another example that isn't the standard graph we've been using from the beginning. Here it is, it's underneath me, it's a 6-node graph with 7 edges. And what I've done is I've set node 6 to ground, 0 voltage, and I've put node 1 at unit voltage, and I'm going to insist that KCL, Kirchhoff's current law, holds at nodes 2, 3, 4, and 5. The question is then, what is the effective conductance of this circuit with these 2 nodes identified as kind of the plus and minus node? Okay. It's a good example because it allows us to put some ideas into practice here. Well, if in doubt, you can always use the kind of matrix linear algebra approach that I've already encouraged you to do. And in general, that's what you have to do. Okay, so in this case, you see what would happen is you could write down, remember, this is the key equation. You've got, by the way, I didn't tell you about the conductances. The conductances of all these edges is 1. Okay, and in which case we have K, which would be AT times A, because all the essentially this is ATC times A, where C is the conductance matrix, but the conductance matrix is the identity, so I didn't even bother to write it. Okay, so with K is equal to that, or actually let's just write it down. This is another little exercise for us. Let's just work this one out. Well, remember K will be n by n, where n is the number of nodes, so it looks like in this case it's going to have 6 columns and 6 rows. Okay, so it's quite a large matrix. And remember what the rule is. What you do is you look at how many edges are connected to node 1. It's 2, and then you put a -1 in the nodes to which it's connected. Zeros everywhere else. Let's do 2. 2 has 3 nodes connected to it. Right, and it's also connected to node 1, node 3, and node 5, not to the others. Node 3 has 2 edges from it with a 2 and a 6 connected to it. And then node 4 has got 2 edges with a -1 and a -5. The rest are zeros. Node 5 has 3 edges connected to it. It's connected to node 6. What is that? Node 2 and node 4. Okay. And then node 6 has 2 edges connected to it, and that's 5 and 3. So there's the Laplacian if you wanted to look at the full Laplacian. And then remember the key equation. The key equation is K times X is equal to F. Okay, and F will be remember we're the current divergent. The current divergent from node 1 will be the effective conductance. And then we've got 4 nodes where KCL holds, and we must have minus CF into node 6. Okay, and remember that this K is singular. It has x naught as 1, 1, 1, 1, 1, 1 as a right eigenvector, and the only right eigenvector because this is a connected graph. And we could ground node 6. So we could, in this 6 by 6 matrix, we could ground. We've grounded node 6, and we could also delete the column and row 6. Okay. And then we would have a K hat, what I call a reduced Laplacian and a reduced system. This is the reduced system. And we could use Schur complements to find this. You see, what would happen, here's how I would do this. I'll just indicate this. I'm going to leave this as an exercise because I don't want to do it this way. You can do it this way. If I ground this, here's my full Laplacian. If I decide to get rid of column 6 and row 6, then this is my K hat. Okay, and then what I can do, of course, that's K hat, and then the point is that in the first component there's also an unknown, so I would do a subblock decomposition and let this be a subblock, this be a subblock, and I would split it up like that and use Schur complements. Okay, I've only sketched that out for you, and I'm going to leave that approach as an exercise. The reason being, that I want to do it a different way. So I'd like to do this a different way and use some of the tools that I've introduced to you to kind of simplify this so that I don't have to do it on MATLAB. Maybe I can do it by hand if I've used enough thought. Well, I've noticed, if I just stare at that picture below me, the circuit, that aren't edges C and F two unit conductance conductors in series between nodes 1 and 5? And similarly for nodes, edges B and C between nodes 2 and 6? So I'm going to introduce my squiggly arrow because I've only been asked for the effective conductance. So let me reduce it, this complicated circuit, to a simpler equivalent circuit. What I'm going to do is I'm going to keep nodes 1 and 2, 5 and 6, and then I'm going to keep those edges. But as I said, C and F are like two edges. Remember my little pink boxes? I'm going to introduce an effective edge between these two. And what's their conductance? I use my rule for two conductors in series. It's 1 times 1 over 1 plus 1, which is a half. Same over here. So now, for the purposes of working out the effective conductance, I can redraw my effective circuit, okay, to be this. Okay, and now what I'm going to do is I'm going to draw on the edges the values of the conductances. So now this is my x1 is 1 and this is my x6 is 0. So now this is my, if you like, the effective circuit that I should consider and work out the effective conductance of this. So this is better, isn't it? Because this has only got 4 nodes. So the size of all of my Laplacians and weighted Laplacians is going to be smaller. That's got to help me. Okay, I know that my fundamental equation is always this. Okay, this relates the divergences of the currents F at the nodes with the voltage potentials at the nodes X. So what's my weighted Laplacian here? Well, I didn't tell you this trick if you've got, I left it as an exercise. Let's keep the node labeling we've already got, even though they don't go in sequence anymore, because nodes, 3 and 4 have disappeared. This is, of course, 4 by 4 now. Now what you do, and you can, it's an exercise to check this is always true. What you do is you go to each node and you look at, so if I'm at node 1, look, I add up the conductances. I used to just add up the number of edges, but now they're weighted. So I add up the weighted conductance of all the edges, which is just 1 plus a half, which is 3 over 2. And then because it connects, this is node 2, this is node 5, and this is node 6. Okay, then I put a minus 1 in there and a minus a half in node 5, and it doesn't go through node 6. Okay, it's not connected directly to node 6. Then I go to 2, and I've got a total of 5 over 2 conductance from there, and I go to minus, it's connected by minus 1 to the first node, by, what is that, minus 1 to the 5th node and minus a half, and then I carry on. 5 also has a total of 5 over 2. It's minus 1 to node 6, it's minus 1 to node 2, and it's minus a half to node 1. And then I've got 3 over 2 in node 6, and it's minus 1 to node 5, and minus a half to node 2, and it doesn't go near 2. So there's my weighted Laplacian. Notice I didn't do it by computing the incidence matrix, the conductance matrix. I just worked it out by that little trick. Check that trick is always true. Okay, that's a little exercise. Now, we know, don't we, that this is a right null vector of this weighted Laplacian. Okay, so this is a singular matrix, so we can't just invert K to solve for the things we need to know. But what we can do is we can just kind of eliminate one of the columns and rows. So let's choose to just eliminate row 6 and column 6, okay? And then that leaves us with a smaller system. In fact, it leaves us, I think I put hats on it before. Okay, and in fact, let me just write this down. It's going to be 3 over 2 minus 1 minus a half. It's going to be minus 1, 5 over 2 minus 1 minus a half minus 1, 5 over 2. Now, what's my unknown? Well, I know that the voltage at node 1 is 1. I don't know the voltages at 2 and 5. And I also know, no, CF is the value that I'm looking for. And then Kirchhoff current law holds at nodes 2 and 5. So this, of course, is the linear system that I've reduced the problem to. And you'll see again that, look, here are two of my unknowns and here's another one. So now this smacks of the Schur complement method that I've already suggested to you. So let's use Schur complements. As usual in the way I've already indicated. And it's in this case, it's so easy because it's only basically involves the inversion of a 2 by 2 matrix, which anybody can do. And so turns out I'm just going to give you the answer. The calculation is an exercise. The answer that you will find if you do that is 5/7. So the effective conductance of this circuit underneath me is in fact 5/7, and quite apart from inverting, had I not done the reductions using the simple, these two things here, if I had not done these reductions, the size of my matrix would have been 4 by 4 to invert, which is hard work. If you do it, you can do it by hand, but who wants to? You just use MATLAB. It will work. So here's a double exercise. Use MATLAB to do it using Schur complements on the original Laplacian, of course, reduced by a row and a column. And then solve this system that I've written down here, where I've used my little reduction to equivalent circuits idea to make it a smaller dimension. And you should always bear in mind that that's a good thing to do. If you can reduce the dimension of a system, it's always good in applied mathematics. Okay.